The chain rule is by far the most important derivative rule we're going to do. If I lose you at any point in time, you're going to let me know. We'll start with the derivative of x squared plus 1 with 100, and we'll just do it by brute force, not using the chain. We'd have to write it out 100 times and use the product rule 100 times, as in derivative of first times everything else, derivative of second times everything else, derivative of third times everything else, and so on. Derivative of first would give us 2x. Everything else, there'd be 99 of those. The same thing would be true for the derivative of second times the rest, derivative of third times the rest, derivative of fourth times the rest. And how many of these terms would we have? If we started with 100 of them, we'd end up with 100 of those terms. So this is our answer for the derivative. That's done by brute force. Let's see what happens when we try the chain. When we try the chain rule, the idea is this. If you had meters per hour and your goal was to get meters per second, you'd multiply by hours per second and you'd end up getting meters per second. We want the derivative of y with respect to x. That's just another notation for y prime. So we could do derivative of y with respect to whatever we want, then multiply by that derivative with respect to x. It gives us the exact same answer. So the whatever we want is going to be whatever it's convenient to do with respect to. And so let's take this derivative, and we're going to do it with respect to x squared plus 1, then multiply by that derivative with respect to x. And why did we pick x squared plus 1? If we have an x squared plus 1 here that we pretend is our a, that means that becomes derivative of a with respect to 100. How does that help us? What is the derivative of a to the 100 if a is your variable? Well, that would just be 100a to the 99. And derivative of x squared is 2x. Okay, well, we didn't have a in the question beginning. Okay, so we'll just resubstitute. We put a in place of x squared plus 1. And then we clean it up, and we end up with the exact same answer. Okay, how did that work again? So we wanted to find this derivative with respect to x. So we said, let's take it with respect to something that allows us to do a substitution. So essentially, whatever's in brackets. Then we have to chain that with that derivative with respect to x, and we're chaining that so we end up getting what we want in the end. So whatever's here has to go there so that they eliminate each other and you end up with the same rate. Okay, derivative of a to the 100 was just 100a to the 99. A stood for x squared plus 1, and we get the same answer. Let's try another. So this one, we're going to take the derivative with respect to what's in brackets and then take that derivative with respect to x. That allows us to make the following substitution. So we wrote down derivative of y, this is just y, with respect to what's in brackets, and then we write that down here so that the effect is that you chain your derivatives and you end up with a derivative with respect to x. Okay, we said let this be replaced with a, derivative of a to the 12, 12a to the 11, derivative of 5x plus 7x minus 1 is 10x plus 7. And then you resubstitute. A stood for 5x squared plus 7x minus 1. And that's it. We can't do anything else with it. Let's try another one. Square root of x squared minus 1. I would write that to the 1/2. We'll take the derivative with respect to what's in brackets, multiply by that derivative with respect to x. Replace those with a. If you're having trouble knowing what to let a equal, I'm just saying everything in this denominator is a, and so this is what a becomes. So I've got a to the 1/2. Derivative of a to the 1/2, normal derivative, 1/2 a to the negative 1/2. Derivative of x squared is 2x. A stood for x squared minus 1. 1/2 of 2x is just x. And then we really don't like negative exponents. At least this part of we doesn't. So I would put it in the denominator as x squared minus 1 to the positive 1/2. And again, the reason I'm doing this, imagine if this turned out to be, say, 4 to the negative 1/2. We're not that good at that, but we're fine if it's down here. 4 to the 1/2 is just 2. We'd know the answer. So that's why we're in the habit of making these positive exponents. And even better, make it a square root. For those who are looking at this going, I don't really like this, there's another way of thinking of it. The other way of thinking of it is take the derivative of the outside function. Derivative of something to the 12 is 12 something to the 11. And then take derivative of the inside function. Derivative of inside function, 10x plus 7. Try that again. Outside function, a half something to the negative 1/2. Inside function, 2x. So some of you might prefer that. Let's try another one. Don't worry about that. Derivative of sine. I would say, let's replace the angle, 3x plus 7, with an a, and then chain the derivative of the angle with respect to x. Okay, derivative of sine of angle is cosine angle. We know that rule. Derivative of 3x to the 7 is 21x to the 6. And then, what did a stand for? Well, that was our angle. And then we tend to put that at the front. Why we do that? The way it's written, it's not clear if you want me to multiply those together and then find the cosine, or is it really written like this? So to make it incredibly clear, we put it up front. So what just happened? Took the derivative with respect to the angle, derivative of angle with respect to x. Derivative of sine of angle. Derivative of sine is cos of angle. Took derivative of angle, replace the angle, put the derivative up front. Well, those are like the idea of outside and inside. Derivative of outside function sine is cosine of angle. Derivative of inside function, 21x to the 6. When you're doing this, if you want to do a really super quick check of your work, I like to check my angles. If they have changed throughout the question, something's gone badly wrong. So you go angle, angle, that looks good. So the angles don't change. The only way they would change is if you use a trig substitution. So that's kind of university law. Okay, this one's fairly demanding. Tangent cubed, what does that mean? So when you see sine squared x, that means you are squaring the sine of x. Okay, so sine squared x is sine x squared. So tan cubed is the tangent of the angle cubed. This derivative, there's 3 steps. Why is that? We have the function cubing, and then we have the trig function, and then we have to multiply by the derivative of the angle. So what did we do? We said all of this was cubed. I'm going to replace that with a. Then we put that up here, and when you do trig, you do it with respect to angle. And I'm using b just because I've used a already. And then we have to put the angle up here and take the derivative. Whew. But this is nice and easy once we've got it written this way. This just says, what's the derivative of a cubed? We know that. Derivative of tangent of angle, we know that. Derivative of angle, we know that. And then just a was tangent of 5x minus 7, and b was 5x minus 7. Clean it up, put the 5 with the 3, and we've got 15 tan squared 5x minus 7 secant squared 5x minus 7. If you want to try that, going from outside in, it's a little more complicated. So the outside function, raising something to the power of 3. Bring the 3 down, leave the bracket alone, lower the power by 1. So that would be 3 tan squared 5x minus 7. Derivative of inside, derivative of tan is secant squared angle, and then derivative of super inside is 5. So I like to use this notation because then I know exactly when I need to stop. My goal at the end, take the derivative with respect to x. So I know that when I get down to x, I am done. For those who do outside and inside, you just really have to know what you're doing. So be careful. All right, what do we have today? Lots of questions. Do every single one of them. Will it take time? Yes. Does this notation take time? Yes. But it can simplify things and make your life easier. So you might be a little bit frightened. This is kind of new. Take your time. It gets better, but really learn.